Now let us see what is called as the chain rule for finding out the derivative of the composite functions. If y is a differentiable function of u and if u is a differentiable function of x, then dy by dx is equal to dy by du into du by dx. So here y is a composite function of x, and to find the derivative of y with respect to x, we find the derivative of each link in the chain. So since y is directly expressed in terms of u, we find out derivative of y with respect to u and then multiply by derivative of u with respect to x. And this process can be extended to any number of levels in the composite function. So instead of y as a function of u and u as a function of x, suppose we have y as a function of u, u as a function of v, and v as a function of x. That means if we have 3 levels, then there will be 3 terms on the right hand side as shown here. So let us solve few sums based on this chain rule. Find dy by dx where y is given as log of sin x. Now the important trick to find out the derivative using chain rule is that whatever function is given to us, we should describe that from outside to inside. That means what is the outermost function here? As we see, it is a log. Now inside the log we have sin, and then we have the actual variable x. So it is log of sin of x. So therefore to find out dy by dx, see what we do basically is that let us consider this entire sin x as say u. Okay, so if we consider u as sin x, what we get is y is equal to log of u, isn't it? So therefore dy by du gives us derivative of log u with respect to u, which is nothing but 1 upon u, as we know from the standard table. Correct? So therefore dy by du is 1 upon u. Now next we have to find out du by dx as per the chain rule, and since u is sin x, so therefore derivative of sin x with respect to x, as we know, is the cos x, isn't it? So we have found out the individual 2 derivatives in the chain. Now as per the formula, dy by dx is given by dy by du into du by dx, and we have already evaluated the 2 derivatives. The first is dy by du, which is 1 upon u, and second is du by dx, which is cos x. And u is a symbol which we brought on our own, so we must replace everything in terms of x at the end. So 1 upon u is nothing but 1 upon sin x into cos x. So that is ultimately cos x upon sin x, which is nothing but cot x. So that is the required derivative. Now by practice, you will be able to write the derivative using chain rule in a single go. That is, every time it's not needed to show what is u, what is v, and so on. Let us see one more example so that we can practice how we can write the derivative in a single line. Here we have to find dy by dx where y is given as tan square of cosec 5x. Now as I said in the last example, we have to recall and read out the function from the outermost operation to innermost operation. Now one care we have to take here is, although we visually see tan as the first expression written, but that is not the outermost operation. The outermost operation is the squaring operation. So that is a operation which is done at the last. So therefore y is equal to square of tan of cosec of 5x, isn't it? So there are these different levels of composite functions. So therefore to get the derivative of y, if we look at the outermost operation, which is the square operation, Okay, so we have something square. Now if it were x, then the derivative of that would have been 2 into x, isn't it? So therefore something square has the derivative as 2 into that something. So therefore the derivative of the first step is 2 into the tan function. So that is 2 into tan of cosec 5x. Now next is we drop the outermost operation, that is we drop the square. So what remains is tan of cosec 5x. So now here we have the function of the form tan of something. Now we know that the derivative of tan is nothing but sec square. Okay, so therefore we multiply by the next derivative, that is derivative of tan of cosec 5x, which turns out to be sec square of cosec 5x. Now moving ahead, we have not yet reached the variable x, isn't it? So now we drop the tan function also, and inside we have now the cosec function. Now if we recollect, the derivative of cosec of something is minus cosec into cot, correct, using the standard derivative. So therefore here also we have to keep further multiplying by derivative of cosec 5x will be equal to minus cosec 5x into cot 5x, and even when we drop cosec x we are left with 5x. So we have to multiply with the derivative of 5x, which is nothing but simply 5, because we know that 5 is the real constant, so that will come out in the multiplier, and derivative of x is nothing but equal to 1. So therefore in this way, we have used the chain rule in a single line. So we can of course simplify this further, that is 2 multiplied by 5 gives us 10, and we have the minus sign, so that gives us minus 10. Then we write the functions as they are, that is tan of cosec 5x multiplied by sec square of cosec 5x multiplied by cosec 5x cot x, which is the last term. So this is how we use the chain rule. Just to repeat, while we solve the example based on finding out the derivative of a composite function using chain rule, we have to clearly identify which is the outermost operation, then the next inner operation, and next inner operation, and so on, and write down the derivatives of all those functions in successive manner.